So here's our last topic. We are discussing contact fatigue. And this is an interesting sort of add-on to our topic of fatigue. You might think to yourself, oh, I think you might be able to apply some of the things that you did before to this topic. Not really. So this one's a little bit different. For one thing, this is kind of the big difference between the fatigue stuff that we've covered up till now and this particular topic. Contact fatigue does not have something that is an infinite life type equivalent thing. Okay? What we did before with finding an endurance limit, where as long as you don't load above a particular level of stress, you can put as many cycles as you want on something. We do not have a concept like that for any material, even steel. Right? We do not have a concept like that in the case of contact fatigue. So where does this occur? There's a lot of places where this occurs, actually. This occurs anytime you have different pieces of a machine that contact each other. Okay, so some really common examples of this would be like gear teeth. Okay, one tooth contacts another gear tooth, and as it does that, it creates literally surface stresses in between those two parts at the point where they contact. All right. Another example might be ball bearings. You've got little balls that ride in races that go around the outside, and at any point around the outside of the race of that ball bearing, there could be contact between a ball and that point, right? And that creates a contact stress right there at that point. The picture that you see up here is a simulation that I ran so that I could show you what this stress profile looked like, at least roughly, where you have two parts that are contacting. And this, you might look at the actual mesh that I ran, which is over there on the left side. You might look at that mesh and kind of wonder what you're looking at. So basically, this is how I simulated a case where there are two maybe larger cylinders that are contacting one another. And what I did is I chopped out just two little tiny squares right at the point where they contacted each other. And I did that so that I could pack as many elements of material in there as I could and get a little bit better mesh resolution in order to be able to capture what this stress profile looked like. So what you see on the right side is a rough idea of that stress profile. What do you think looks interesting about that stress profile? Okay, say that one more time. Okay, there are some interesting like 45-degree lines maybe that show up on there. The highest stress is not at the point of contact. Okay, this is strange, right? This doesn't seem like that's very intuitive. But this is actually how it works. And there is a specific ramification that happens as a result of this highest stress area being a little bit below the surface. It's not very far below the surface, but it's a little bit below the surface. What happens is the outermost shell of material actually tends to survive okay, but right underneath it, the material that's supporting it is the part that tends to fatigue over time. And what happens whenever a part like this begins to fail in contact fatigue, it actually has little bits of material that would come from these little areas right here. There are little chunks of material that essentially come out, right? And it leaves little tiny holes in the surface of the part, and those holes are often called pits. And you look at a part and you say, it looks like there's some pitting going on the part. And what that means is there's these little, almost look like little pinholes on the surface where material has been coming out, and it does that because it has those high stresses just below the surface of the material. All right? And so this is kind of an interesting thing. It is a phenomena you can actually observe on real gears after they've been taken out of service. You can actually look at the gears, and you can look at the teeth of the gears, and on those teeth you will often find little pits at the points of contact where the gear teeth actually contacted one another. all right? And what's tricky about this is there is no endurance limit, right? So whenever you're designing things that are going to be contacting one another, it really is kind of important for you to figure out what your stress and load levels are so that you can figure out how many cycles you expect for it to last before you have significant pitting. All right, so this is what we're going to do with this, and that's kind of what I put as a little statement right down here. Your stress zone experiences high shearing stresses just below the surface, and that basically causes a fatigue to happen just below the surface, and at some point a little bit of material is expelled from that little zone of high stress, and it creates a little pinhole in the surface of the material. And having a few of those is not a big deal, all right, in most cases. For most parts that pitting might occur, having a few little bits of material that come out is not really that big a deal. But let me ask you, have you ever felt something that had ball bearings in it, and even though, you know, maybe you kept it completely clean where you didn't think any dirt would have gotten into the bearings, yet after a certain amount of life of the machine, or whatever it is that has those bearings in it, the shaft starts to feel rough. Like you start trying to turn it, and turning it doesn't feel as buttery smooth as it did at one point in time. All right? One of the things that may have happened that led to that rough feeling is that you ended up having more pitting than you should, and then that leads to a rough feeling whenever you start turning the shaft for something like a ball bearing. Okay? This is kind of an interesting thing too, because a failure is harder to define when the failure has actually really occurred, right? Failure is generally whenever you have loss of function. Okay? So if you have a ball bearing and it's getting rougher, right? When do you say it has lost function? You know, maybe the thing will still work, it's just got a rough bearing in it, right? So there's some debatability, I guess, about that as well. And the answer to that question is probably going to be an application-specific type of thing. You know, in some cases you might need the rotation to be perfectly smooth, and any roughness at all, you can't really tolerate much at all. Whereas in other cases, it might be just fine. One of the things I think of, when I was 12 years old, I got a paper route, and I delivered papers on rollerblades. You know, picture that. Right? Just right now, superimpose over me, you know, a canvas bag and rollerblades on my feet, and I did that for 5 years. And so over those 5 years of delivering papers, I had to replace the bearings in my rollerblades a lot. And it was interesting, so I've dealt with this a lot because I knew when my bearings were getting close to being in need of replacement, right? And it sort of was an escalating thing. So I became aware of it, but I could still ride on them for a little while, but it got to some point where I knew that there were maybe only 2 or 3 more trips that I could take before I might have disaster, right? I might actually have balls coming out of the bearing or something like that. So anyway, that's my best, you know, firsthand experience that I actually physically felt through my feet throughout my childhood, or at least my, you know, my adolescence. All right, so what we're going to do here is solve a problem. This is another example of a place where you have contact stresses. And this is another one that's really common in engineering. It's a case of a cam. All right. Cams are used for a lot of things. They are used to control motion. Usually some sort of cyclic motion is a common way of doing this, although it doesn't have to be. Cams are a way that you can have contact between one surface and another, and based on the profile of the cam, you can create a specified type of motion. All right. So those of you who have already taken MEEN 363, you've probably done a little bit with cams in there. Those of you who haven't, you have a little bit to look forward to now, that you get to study more of the aspects of this that have to do with how to generate certain types of velocity and acceleration and jerk profiles for the cams. That's not really our focus. Our focus right now is surface strength of the cam. Okay? And so we have this thing, it's rotating at 30 RPM. It has a major axis length of 1.5 inches and a minor axis length of 0.6 inches. Okay. it rides against a circular follower. That's sometimes known as a roller follower, right? So some cams have a roller that rides against the cam, and some cams have like a flat surface that rides against the cam. There's a couple of different ways to do that. But this is a roller follower. It is being held against the cam by a spring. And we're presuming that where this rod comes out through this sleeve bearing, we're presuming that there's no additional force happening on the end of that rod. You know, depending on what the application is, that may be a good assumption or it may be not, but we'll just assume that there's not an additional force happening on the other end of this rod. So we're really just overcoming the force of the spring. Okay. The surface of the cam follower here, it's got a Brinell hardness of 510. All right. The spring constant for the spring is 300 pounds per inch. And in the position that you see it shown, it already has 1/10 of an inch of spring deflection. All right, so that means that when it's sitting there right now, it's pushing with a force against the cam of a certain amount due to that 1/10 of an inch of spring deflection. And then face width, that's basically in and out of the page, how wide are the faces that are bearing against each other. It's like how far into the page does the roller go? How far into the page does the cam go? And so there's these surfaces, kind of a line of contact where these two surfaces mate right at that point where they touch. We good so far? Yes, sir.
Just unrelated, what is the purpose of that sleeve bearing?
Just pointing out that often for a case like this, you're going to need something that constrains lateral motion, or in this case vertical motion, of that roller so that it's basically showing you that it's moving in a straight line. Okay, and a sleeve bearing right there is the mechanical element that is holding that rod so that it is just moving in a straight line. Okay, there's not that much significance to it other than that. All right, so we're using a correlation given in 668. So, you know, what we're doing here is I'm setting this up so that you're given all the information that you would need. There are a couple of different ways to do some of these problems, and so I will sometimes give you information about what specifically I want you to use to do the problem. And so these are two pieces of information there. I want you to use a correlation given in 668 and then a beta value of negative 0.055. And we'll figure out as we go along what that means. Okay, what we want to do is find the minimum Brinell hardness we need so that the cam lasts for 2 years of continuous operation with a design factor of 1.2, where our design factor focuses, first of all, on guarding against excessive stress, and then second of all, guarding against excessive force. Okay, so this is actually, let me go back to the picture that I had up here. And I'll do this too, actually. I have a little video where you might see the how that stress develops as the load increases. Okay, you'll notice there, or you might not, but what you should see there is that as the load is applied, the two surfaces actually smash against each other further. There's deformation of those surfaces, and the contact area increases. Okay? So as that happens, it basically, the more deformation there is, the more force it can take. Okay? So there's a nonlinear relationship between force and stress. And that doesn't happen for a lot of the cases that we studied or that we have studied in here so far. But this is a case where we have a nonlinear relationship between force and stress. Okay, and where we see that coming in this particular problem is with equation, you might see equation 666 on page 337. It says that S sub C is equal to C sub P times the square root of F over W 1 over R1 plus 1 over R2. And so you see there, in this case, I don't particularly love, let me just say this right now, I don't particularly love the notation that they use in this section. But basically what this is doing is you are calculating a stress over here for S sub C, and you're doing it based on the equation over here to the right. This is, again, equation 666. All right, and so the main reason I wrote this up here is that I wanted to show you the nonlinear relationship between stress and force. All right. Other things in here, you know, F is just force, W is just the width of the cam, R1 and R2, those are the radiuses, radii, right at the point where the contact is occurring, okay? What does this do in terms of stress? If you have a larger R value, what does that do? Okay, a larger R value will decrease stress, right? So that larger R value is decreasing stress. Does that make sense? What if you had a really, really large R value? That means a large diameter thing, right? It's a big object where it's a, you know, very gradual sloping of the parts. It seems to make sense that that would actually be better at carrying stress, because as it began to deform, the other material would more quickly come in and increase that area where the contact was occurring. Do you agree with that? So that part makes sense. So the question I have, first of all, from this equation is, where is our worst case scenario? Okay. Yeah, the worst case scenario is actually going to be at two locations, right? Because it's a symmetric cam. It's going to be bad right at the peaks of this cam, okay? And that means that one of the things we're going to need to find is the effective radius at those locations in order to handle this problem, okay? Shall we go ahead and do that?
Which one is R1 and which one is R2?
It doesn't actually really matter for our question here. The reason those values have to be in there is that it's part of the equation that predicts how much stress you're going to have as the force changes, and that is going to be a function of what those radius values are due to the fact that it's going to change how the interaction occurs. Okay. In this equation, the other thing you see here is C sub P. Okay. That is not a specific heat value. That is a material constant, and we're going to look at that here in just a second. Okay, so this is our equation we're going to be working with, along with some others. So here's what we need to do. We need to, first of all, I guess, figure out how much force do we have occurring at our worst case scenario. How's about that? Is that a good place to start? Okay. Force at maximum, maybe I'll say at critical location. Okay. So how do I figure this out? Okay. I need to figure out deflection. So my maximum deflection is going to be equal to the 1/10 of an inch I start off with. Okay. Plus what? Okay. Notice here that right now I'm at a radius of 0.3 inches away from the center, right? And it will move as this thing rotates 90 degrees, as the cam rotates 90 degrees, it will move the roller to up to one of these peaks. So basically this thing will rotate to where it's an ellipse that would be acting kind of like this way, or that would be oriented this way, right? And so what I need to do is find the delta of the radius value from where it is now to where it's going to go, right? And so what that's going to be is just how high does it go eventually? What's that radius value from the middle to the outer? 0.75 minus 0.3 inches. Okay, and so this gives me 0.55 inches. Okay, well, what I do with that is I plug it into my spring equation, my Hooke's law, as some people call it, and I'm going to find my maximum force. Okay, for that I've got 300 pounds per inch times 0.55 inches. And that gives me 165 pounds. Okay?
When you did your delta max formula, where did the 0.1 inch come from?
That is from this initial spring deflection that was given. It means that, in the position that it starts out, when the spring is most extended and this roller is touching in the position that was originally shown, then there's already 1/10 of an inch of spring deflection at that point. Okay? All right, so that's one of the things that we need to know. We already know W, right? So now what we've kind of figured out is what do we put in for F? What do we put in for W? Okay. W is just that face width. So that's something I can just directly put into this equation. Okay. We need R1 and R2 though. And I mentioned that a second ago. Let's go ahead and find them. Okay. One of them's easy. We'll say, R1 will be for the follower, and then R2 will be for the cam. Okay, so what's R1? Okay, R1 is just equal to 0.2 inches. What about R2? Well, not all information that you're ever going to need is in Shigley. So where did I go? I went to Wikipedia. Now, I'm not recommending Wikipedia as a blanket statement, but they're usually fairly reliable on things that are, not very debatable, right? So mathematics things, it's usually right. And so let's go ahead and look and see what they have there. Radius of curvature for an ellipse. So on the major axis, it has the smallest radius of curvature, and it's based on b squared over a. Okay, where the major axis has a length of 2a, and the minor axis has a length of 2b. So, the numerator there is for the minor, and the denominator is for the major axis. Okay, so b squared over a. And what we find there is that we have 0.3 inches squared over 0.75 inches. And this gives me a value of 0.12 inches. Okay? So there's a couple other values that we needed. All right. The next one we need to look at is this C sub p term. Okay? C sub p is it's a factor that is just a material property. And it's interesting, it's a function of the elastic properties of a piece of material. And they don't give a nicely encapsulated statement of how to find C sub p. So what we have to do is we actually have to go to a couple of different equations and assemble our own statement of how to find C sub p. First of all, I will say that we have here, it's actually not even listed as an equation, right above 666, there it says here the term where we have 1 minus the Poisson's ratio squared for piece number 1 over the elastic modulus for part number 1 plus 1 minus Poisson's ratio squared for part number 2 over the elastic modulus of part number 2. This whole thing is equal to 1 over pi C sub p squared. Okay, I would have much preferred if they actually had put that more simply than that, but you know, this is how you can calculate this factor of C sub p squared. Okay, so what I'll do is I'll actually rearrange this and say that, that this means that C sub p is equal to a square root of 1 over pi times that expression that was originally on the right, 1 minus your Poisson's ratio for piece number 1 squared over the elastic modulus plus 1 minus Poisson's ratio for part number 2 squared over that elastic modulus. Okay. And this means, so this is actually interesting, you'll notice there are no strength properties listed there. Right? None of the things that I have listed there are properties that are strength of the material. They are all elastic properties. So that means that once I calculate what this is for steel, and you know, this whole course long we've always basically been saying that if it's steel, you're going to have a constant elastic modulus, right? You're going to have a constant Poisson's ratio, a constant modulus of rigidity and that kind of thing, right? So your elastic properties of your materials don't change. And so when I calculate C sub p for steel, which is what both of these parts are, okay, this is kind of a once and for all calculation, right? And it's just going to be equal to the square root of 1 over pi times 1 minus the Poisson's ratio for steel that we have in the back of this book is 0.292. That'll be squared. And this is divided by 30 times 10 to the 6th psi plus 1 minus 0.292 squared over 30 times 10 to the 6th psi. Okay. If you had a situation where you had materials that were dissimilar to one another, right, then you would actually have to put in properties that were different for one part, for one piece versus the other piece. But in our case, we have the same properties for each. This winds up being 72.2475. And the units are interesting here. Square root of KSI. Okay. And that one's hard to interpret what that actually means, right? So I'm not necessarily going to try it. If you interpret it in terms of this expression, then it kind of makes sense. And that the reason for it is the fact, again, that it's a nonlinear expression. You don't have a linear relationship between force and stress. Alrighty, so now we have C sub P. Now we can calculate S sub C. All right, so let's do it. S sub C. It's going to be equal to C sub P. Oh, one other thing, I should mention this as well. We are supposed to apply a design factor of 1.2. Okay, but we're supposed to do that two different ways. One case we're supposed to apply that as a guard against stress, and another one we're supposed to do it as a guard against force. Okay, here's what that means. Basically, if you want to use your factor of safety, or your design factor as they're calling it here, if you want to use that in such a way as you can essentially, let's say you came up with a design factor of 1.5, doing this problem the other way, like you weren't specifying a design factor, you calculated one, you wound up with a number, and you came up with 1.5. If you do it as something guarding against excessive force, and you have 1.5, then you can take that 1.5 and multiply it by your force that you use to get that, that factor or design factor, and that should be how much force you should really be able to put on there before it fails, right? So that's what that would mean in that case, whereas you have to apply it differently if you want to figure out essentially the ratio of stress, of strength to stress, right? So you're applying it against excessive stress rather than excessive force. So we have two different ways that we can apply that factor of safety. It is discussed down at the bottom of page 337 how you do that. And basically what it comes down to is whether or not you take the square root of the factor of safety. And so what I'm going to do here is first show you the one where you're guarding against excessive stress. This is the one that does not include the square root. Okay, so kind of where we would add this extra term for the factor of safety / design factor is right here. Okay, and if you put it in just as a factor like this, this is what you do for the case where you need to guard against excessive stress. But if you need to guard against excessive force, you take the square root of it. Okay, so we'll do those two different cases here. So we'll take 1.2 times 72.2475 square root of KSI. Okay, multiplied by the square root of 165 pounds over the face width of 0.5 inches. This will now be multiplied by 1 over 0.2 inches plus 1 over 0.12 inches from our two radius values we got a second ago. Okay. And in order to make the units consistent here, we would also want to convert. Right now we would have this in PSI, correct? So I want to make it consistent with the KSI I have over here, and so I'm going to multiply by a kip per 1,000 pounds. All right, so this S sub C value focused on guarding against excessive stress is going to be, let's see, 181.86 KSI. And what if I want to guard against excessive force? Well, it's very similar. What we do in this case is we take a square root of 1.2 and the rest of it stays the same. All right. And when I plug all of that in, we get an S sub C value focused on guarding against excessive force of I've got 166, and that page cut off right in the wrong spot. Let's see here. 166.012 KSI. Okay. So what? Right? We've got S sub C. It's time for us to talk about what this means. Okay. S sub C is basically a surface contact strength, all right? And what we have just calculated for is the surface contact strength that we need at however many cycles we need it. We haven't figured that out yet, right? So we are given enough information in this problem based on the speed that the cam is rotating and how long it has to do it. It has to last for 2 whole years of continuous operation, moving at 30 RPM. We know how many cycles it's got to last, right? And so at that number of cycles, this is the strength value, or these 2 strength values, depending on how we want to calculate it, right? These are the 2 strength values that we need to shoot for, one in the case of stress, of guarding against stress, one in the case of guarding against force, right? But these are based on a particular number of cycles. So let's figure out what that number of cycles is before we move on too much further. Okay, so to kind of put a heading on these are our needed surface contact strengths. Okay, and then we're going to now come up with a number of cycles. And this is how many cycles we need it to last. All right, so we have 30 RPM. That's 30 revolutions per minute. If I take that, how many stress cycles do I have on one of my peaks per revolution? Okay. This could be a little bit tricky. You know, if you're not thinking about it too much, you might say 2. Okay. But if you actually think about it, each of them experiences its own stress, right? So there aren't 2. Each one of them only experiences 1 per revolution. All right, so the number of revolutions is really the same as the number of stress cycles that you're going to have on a particular point on the material. Okay, so that just means that we need to take this and multiply it by 2 years, and that'll give us the number of cycles. Well, those units don't jive all by themselves, and so we need to do a few conversions as well. Okay. So we basically need to take our minute and turn it into an hour, like this. Okay, 60 minutes. Okay, there's 24 hours in a day. I'll get this right at some point. And then there are 365 days in a year. And this gives us the number of cycles that we need for this part to last. So that number of cycles winds up being 31,500,000 536,000. Okay, so here's the thing. What we have just found, we found our the needed surface contact strengths for that number of cycles. All right? Here's the problem. What we ultimately need to come up with is how much Brinell hardness do we need? Okay? So we need some sort of a relationship between Brinell hardness and surface strength, right? Fortunately, we have one, but it requires that we're going to have to correct for numbers of cycles. Okay? So if you look down here, equation 668 is in approximately the middle of the page. And in the U.S. system of units, it says that your surface strength value at 10 to the 8th cycles is going to be given by 0.4 times your Brinell hardness minus 10 KSI. Okay, so this is equation 668. So what does that mean? It says S sub C that you have at 10 to the 8th cycles is going to be equal to 0.4 times your Brinell hardness minus 10 KSI. Okay. The problem for us is we don't need this for 10 to the 8th cycles. We need it for 31,536,000 cycles. Okay? And so that changes what our needed value is for our Brinell hardness, because we may not need it for the same number of cycles. Well, so how do we do that? Okay. Fortunately, we have another relationship that allows us to find a relationship between these two strength values, and it is based on an equation. Again, it's an unnumbered equation. I apologize. It's about a third of the way down on page 337. It says that S sub C is equal to alpha times n to the beta. And a good news for us, a beta value there ends up being pretty constant. Even though there are a couple of different forms of it that might be published in a couple different places, that's why I gave it to you at the beginning. Use a beta value of negative 0.055. Okay? That's a number that doesn't really tend to move much as long as you're talking about steel. Okay, so we have negative 0.055 for beta. Okay, well, so what? Okay, it allows us to solve for alpha, because what we know here is that, or it makes a relationship anyway. What we know is that we can relate Brinell hardness to this surface strength at 10 to the 8th cycles, right? And so what we can actually do is we know the surface strength we need at the number of cycles that we need, so that we can calculate alpha and then plug that in to an equation where n then gets moved to 10 to the 8th cycles, and use the same alpha and beta to figure out S sub C. So that's where we're going to go with this. Without further ado, let's do that. Okay, so finding alpha. My kids like to watch How to Train Your Dragon, so he kind of found his alpha, right? Anyway. Sorry, I'm reaching here. All right, so what we'll do here is we will say that guarding against stress, we have 181.86. 181.86 KSI is equal to alpha, and I'll put a subscript on alpha. This is alpha for the case where we care about stress, times the number of cycles that we had there, 536,000, time, or to the beta, to the negative 0.055. Okay, and you can solve for alpha. And I come up with 470.09 KSI. Okay, we could then do another one of these if we are guarding against excessive force. So that would be, the value we had down here was 166.012 KSI. This is going to be equal to alpha guarding against force. Again, the same number of cycles, 31,536. Again, I messed it up, 31,536,000 to the negative 0.055. And from here, your alpha as it pertains to force instead of stress is equal to 429.13 KSI. Almost there. What do we need to do now? Okay. Plug in these alpha values and the n values to find S sub c. Okay, so we're finding S sub c values at 10 to the 8th cycles instead of 31 million cycles. Okay, so we plug in and say S sub c as it relates to stress is going to be equal to 470.09 KSI times 10 to the 8th to the negative 0.055. And this gives me 170.7 KSI. Okay. If we're guarding against excessive force, then what this gives me is 429.13 KSI times 10 to the 8th to the negative 0.055. And this ends up giving me 155.8 KSI. But we're still not to Brinell hardness, but we're real close. Okay, what do we need to do now? Okay. Use equation 668. Okay. And it basically tells us here that H sub B is going to be equal to our S sub C value. Okay. So H sub B for the case where we're guarding against excessive stress. Okay, it'll be equal to that plus well, let's see, it'll be equal to S sub c at 10 to the 8th, which is 170.7. Plus 10 KSI divided by 0.4. So I want, if I'm guarding against excessive stress, I want 451.7 as my Brinell hardness number. Okay. And the only thing that changes for when we go to force is we're going to do 155 instead of 170.5 or 0.7. And that gives me 414.5. This stuff's a little weird, okay? I mean, I'll say that kind of unraveling these couple of pages of the textbook is not easy on your own. It doesn't make a lot of sense on your own. And so I highly recommend that you make sure you understand each of the steps that we did right here. Basically, I kind of did this problem backwards from a lot of the problems that you might expect to see out of a textbook or something with respect to this kind of work. But you know, you can do that, right? If you want to do it as kind of a design problem and figure out what kind of a hardness number you need, you can go this direction and come up with what those answers are. Anyone have any questions? Yes, sir.
The first step that we took,
yes.
finding the delta max, I didn't get that.
All the way down here.
Yeah.
Okay.
So I know that 0.1 inches for, like, it's already, but what about the second one?
Okay. What we're doing here is understanding that this point of contact is in the position it's shown. It's already spaced at a radius value of 0.3 inches. So this right here is 0.3 inches. Okay, and so that's not any additional deflection or anything. That's where it's sitting when it has a deflection of 0.1 inch. Okay, the radius value up to this point is 0.75 inches. Okay, and what we need to know is the difference between those two in order to add that to the deflection that the spring already has when it's in the position it's shown. Right? So it has 1/10 of an inch of deflection where it's sitting right now, and then we need to add to that the difference in deflection that happens from where it's sitting right now up to the peak of the cam. Right? Anything else? Yes, sir. It is a unitless quantity, which means that their equation there doesn't necessarily make a lot of sense, right? If you really wanted to do that, do this equation well, you would probably actually put in here, whoops. You'd actually put in here a unit for your 0.4. Well, I would do it. You'd put in a unit of KSI for 0.4. Right? There's kind of an implied unit there that is not actually given in the text, but the presumption is that you're talking about units in KSI. Okay? And that would make sense if you went down here and you said apply a KSI here and a KSI here. Right? That makes it work. Right? They just left it out of the text.
Do you need another equation if you're doing metric units?
Yes, and actually 668 includes a version there for SI units instead of US units. Anything else? All right. Well, thank you for your attention, and I will see you next time for the last meeting before the big event.